temperature. It's getting hot in here because it's time for chemistry. Temperature is defined as the average kinetic energy. We all know what temperature is, describes how hot and cold something is, but in chemistry, the formal definition, or actually in physics too, it is the average kinetic energy. Now, all particles are in constant motion, so if you take all the energy that's generated from molecular motion and averaged it out, that is to say, you take every particle's energy, add them all together, then divide it by the total number of particles you have, you will get temperature. As observed in Charles' Law lab, we know that if we increase temperature, that means that we are increasing the total kinetic energy of the sample, which means that more particles are hitting against their containers more frequently, which means a high pressure if the container is non-flexible. We also know that if you change the container to a flexible one, then as you increase temperature, as the particles hit their container wall, that gives the container an extra push, which would allow an expansion or increase in volume. Let's talk about the scales that we use to measure temperature. Now, because we are in Canada and we belong to the 95% population that uses the metric system, we use the Celsius scale. And the Celsius scale is an invention. We made it up. We created it by defining 0 as the point at which water freezes and 100 as the point at which water boils. And then we just separated the 2 points with an equal amount, with equal distant increments going from 0 to 100. The Celsius scale is pretty useful, but in chemistry it's actually more useful to use another scale called the Kelvin scale. The Kelvin scale, or otherwise known as absolute zero, that's a big scary word, eh? Absolute zero. It is the point at which all molecular motion stops. What that means is, if theoretically there was a way to make all particles stop moving entirely, we would call that 0. In AP Chemistry, you will get a more specific, more correct, I guess, definition of that. But for now, it's enough for us to go forward just knowing that 0 is defined as when there are no more particles moving around. Okay. Now, the degrees in Kelvin is actually a little bit off from Celsius. Hopefully you guys did the critical thinking question on your Charles' Law lab and you figured out what degree in Kelvin is equivalent to in Celsius. And you should have found that degrees in Kelvin is calculated by just shifting the Celsius scale by 273 degrees. That number is a measured value. It is not a defined value. It does carry sig figs with it. It's actually 273 point something something. For Chem 11 though, 273 is enough for our calculations. Okay, so let's have a look at the picture of that. So on the right here, there is a comparison of the Kelvin and the Celsius scale. And what you'll notice is that the increment size is the same. For example, if you go from 40 degrees to 50 degrees, that is a change in 10 degrees in size. If you go from 313 to 323, that is also a 10 degree in size. So what we're saying is that the two scales have the same incremental change. However, the point at which they start, the point that is 0 is different. Okay, so where the Celsius scale is 0, the Kelvin scale is at 273.15. That's not a comma, it's a decimal. The graphic was poorly designed. They weren't thinking about formatting. Okay, and so we can probably see that the degrees in Kelvin should be equal to the degrees in Celsius plus 273. The two scales are the same, it's just one is shifted upwards by 273 degrees. Okay? Just for interest's sake, I do have on the left side a comparison of Fahrenheit and Celsius. Now, Fahrenheit was created a long time ago, and it is not based on the physical changes of water. It was based on the physical changes of salt, a saltwater mixture. And the scientists who did that had a good reason for choosing salt. I will leave you to read about it on Wikipedia, should your curiosity pique. Anyways, we see here that the point at which we call 0 on the Celsius scale is called 32 on the Fahrenheit scale. And if we look at the increment changes, they are not the same. For example, if you go from 40 to 50 on the Celsius scale, that is a change of 10. But if you go the same distance on the Fahrenheit scale, that is a change of 18. Which means that to convert from one scale to the other, we not only have to think about the 32-degree shift that two scales are offset by, but we also have to think about how the increments are different size. Okay? So because the increments are different, to convert one from the other, we need a conversion factor. Okay? But that is easy to deal with. We've been doing that the whole year with our unit conversions. Can you think about what the conversion factor may be? Did you get it? The conversion factor should be equal to 10 degrees Celsius over 18 degrees Fahrenheit. Make sense? Perfect. So that means that to go from Fahrenheit to Celsius or Celsius to Fahrenheit, we have to, have our star number be converted by a conversion factor, and then we have to add 32 somewhere. I will leave that to you as a critical thinking question to figure out what the formula is to go back and forth. Okay? One last thing to note about these scales, a degree change in Celsius. So if you went from 0 degrees to 1 degree in a Celsius scale, that would feel the same as if we went from 273 to 274, okay? Because a 1 incremental change is the same, whereas in Fahrenheit, a 1 degree change in Celsius does not feel the same as a 1 degree change in Fahrenheit. All right, let's practice. What is 25 degrees Celsius in Kelvin? Well, we know that Kelvin is equals to Celsius plus 273. So all we have to do here is go 25 degrees plus 273. Okay, and that should equal to 298 kelvins. Let's go backwards. What is 0 degrees Kelvin into degrees Celsius? Well, then instead of adding 273, we will go backwards. 0 minus 273, and you will get to negative 273 degrees Celsius, which was that x-intercept that you found on your Charles Law lab. And lastly, what is negative 32 degrees Celsius in Kelvin? Kelvin is equal to Celsius plus 273, so negative 32 plus 273, you should get 241 kelvins. Moving on to Charles' law. Monsieur Jacques Charles, we did a lab on that guy, and he was looking at 3 variables: pressure, temperature, and volume. We saw the relationship between pressure and temperature when we had our water bath set up, and we saw also the relationship between volume and temperature through our balloon hot water demo and liquid nitrogen. So from that lab, we have concluded that mathematically speaking, when we take volume and we divide it by temperature, we get a constant. That was one relationship that came out of our lab. This should make sense because as you increase temperature, the particles gain more energy, and if they do that, they will collide more with the container, and if the container is flexible, as is the case here in our graphic, we have a little piston that is able to move up and down, then the particles should exert enough force to push the piston upwards. So as temperature increases, volume does so as well. As the temperature decreases, the particles lose their kinetic energy, and so they don't hit against the container as often. There's less force, so the container will shrink back down. mathematically speaking, if volume divided by temperature is equal to a constant, it should make sense that if you increase one, for example, temperature, then to maintain the value of that fraction, volume must also increase proportionally as well. All right. Very similarly to Boyle's law, we can set up a relationship to examine a system before and after a change in either temperature or volume. Here we have the system before. If volume 1 over temperature 1 is equal to a constant, and then we mess with the temperature such that the volume changes according to the temperature change, and V2 over T2 is a constant, and the constant is equal to a constant, so then we get the relationship V1 over T1 is equal to V2 over T2. Very similar to Boyle's law, where the system before is equal to the system after in terms of two variables, assuming that all other variables are kept constant. Let's do an example. If a sample gas measures 2 liters at 25 degrees Celsius, what is its volume at 50 degrees Celsius if pressure remains constant? Well, we know our formula is V1 over T1 equals to V2 over T2. We just plug and chug. The only thing to be careful of is this temperature unit. Because all our formulas are derived with the Kelvin scale, anytime you see Celsius, you must convert into kelvins, okay? So in this case, V1 is 2 liters, T1 is 298. Remember that kelvins is equal to Celsius plus 273. And this should equal to our final volume, V2, over 323. If we are nitpicky about sig figs, and we are, let's be honest, let's have a look at that 323. This Celsius here, 50 degrees Celsius, is only 1 sig fig, and that is being added to 273. Sig fig review. If we were to add these two numbers like we do in grade school, we line them up, we see that the uncertain digit in 273 is the 3. The uncertain digit in 50 is actually the 5 because the 0 is a rounded figure. Okay, so if we were to then follow up and do the addition, and we get 323, our final answer now has two uncertain digits. This 3, because of that 3, is uncertain, and also this 2, because of that 5. And in every final number that we get from a calculation, we are only allowed to report one uncertain digit, which means that 323 is actually a 2 sig fig number. Once again, my particular strategy for remembering sig fig is I like to write numbers as a subscript when they are non-significant. This reminds me of how many sig figs I should carry to my final answer. But of course, in my calculator, I'm going to type in 323 when I when I multiply the other side by 323, just so that I don't lose accuracy. So, final answer then with 2 sig figs is 2.2 liters. Okay, last example. If a sample of gas measures 500 centimeters cubed, whoa, what's that? Centimeters cubed? Oh, throwing you a curveball there. Let's refresh our memory. What is a centimeter cubed? Well, that is actually the definition of a milliliter. That was exciting. All right. What is its volume at, what is its volume of 101.3 kilopascals and 34 degrees Celsius? Typo there. Oh, here we go. V1 over T1 is equal to V2 over T2. Our V1 here is 500, either centimeters cubed or milliliter, your choice. Maybe I'll just keep that here just in case, because that's the original question. T1. What is T1? Well, it says here that it's STP. Let's remind ourselves what STP stands for. Standard temperature is 0 degrees Celsius. So that would make my T1 equal to 273 kelvins. V2 is what we are solving for, and T2 is 34 degrees Celsius. 34 degrees Celsius in kelvins is 307 kelvins. You might be wondering, what is that number for? Well, that tells you that the pressure afterwards is 101.3 kilopascals, and from our STP value in the beginning, we know that the standard temperature is 101.3 kilopascals. So this number here, really, its purpose is to just remind you that we can use this formula over here because pressure is being held constant. Okay? Alright, 3 sig figs, punch it in, chug it out, 562 milliliters. Oh, or if we want to be extra fancy, centimeters cubed. Okay, really, I would also accept 562 milliliters, or if you're extra, you can go ahead to SI units for 0.562 liters, whichever you like. Looking ahead, our next section is combined gas law. Combined? What are we combining? I wonder what that means. Stay tuned for our next time. Goo out.